Hey everyone, and welcome. Let's think about this for a second. Every time you stream a movie, ask an AI a question, or even just search for something, you're tapping into this global network of absolutely massive, power-hungry buildings we call data centers. Today, we're going to pull back the curtain on the huge and frankly often hidden environmental cost of our digital lives, and we'll explore the incredible race to build a truly sustainable cloud. So, let's dive in.
So let's start with a question for you. Think about the last time you went down an AI rabbit hole, or the show you just binged in 4K. It feels like nothing, right? It's just data. It's weightless. But every single one of those clicks has a real physical footprint. It's consuming a shocking amount of energy and water. The big question is, just how big is that footprint really? Well, get this. Right now, data centers, the engines of our entire digital world, are already chewing through an estimated 4.4% of all the electricity generated on the entire planet. That is more than many entire countries use. It's a truly staggering number, and honestly, it's just the beginning of the story.
And that already massive demand, it's on a completely explosive trajectory. Thanks to the unbelievable computing power needed for artificial intelligence, that demand just in the US is on track to double, maybe even triple in the next 10 years. We are standing at the bottom of an energy consumption mountain, and we're about to start running up it like crazy.
So how in the world do we tackle a problem this big? Well, in this explainer, we're going to break down the battle for a green cloud. First, we'll look at how we even measure the problem. Then, we'll get into the hunt for clean power, the revolution that's happening in cooling these super hot machines, how smart algorithms can actually fight carbon, and of course, the hidden environmental cost of building the hardware itself. Finally, we'll put it all together and map out the road ahead.
All right, Section 1, the cloud's insatiable appetite. To solve a problem, you first have to measure it the right way. For years, the industry was focused on one thing, but we're about to see how the goalposts have totally shifted from just being efficient to being genuinely clean.
For the longest time, this was the gold standard, power usage effectiveness, or PUE. It's actually a pretty simple ratio. It just measures how much power goes into the entire building for stuff like cooling and lights versus how much power actually makes it to the computers. A perfect score is 1.0, which means zero energy is wasted on anything else. And for a while, the whole game was just to get that PUE number as low as humanly possible.
But here's the massive, critical flaw in that thinking. PUE tells you how efficiently you're using the power, right? But it tells you absolutely nothing about where that power is coming from. You could have a world-class, super efficient PUE of 1.1, but if your electricity is coming from a coal-fired power plant, you're still a gigantic carbon problem. Efficiency is not the same as sustainability.
So the industry needed a much smarter metric. Enter carbon usage effectiveness, or CUE. And this marks a huge shift in focus. Instead of just looking at efficiency, CUE directly measures the carbon dioxide emissions you're producing for every single watt of energy the computers use. It forces you to look at how clean or dirty the local power grid is, which, by the way, changes all the time. This is the number that really truly matters for decarbonization.
And this table really lays it all out. We've gone from PUE, which is all about energy efficiency, to CUE, which targets actual carbon neutrality. Yeah, there are other important ones too, like WEU for water usage, because some cooling methods use millions of gallons, and ERF for reusing waste heat. But the main takeaway is this huge strategic pivot. The goal is no longer just about tweaking your PUE. It's about crushing your CUE score as close to zero as possible.
And that leads us perfectly into Section 2, the quest for clean power. Because, hey, to get a low CU score, you obviously need clean energy. This is the first and by far the biggest front in this battle, decarbonizing the absolutely massive, nonstop river of electricity that these data centers need to survive.
Now, this right here is a really important distinction you need to understand. For years, you've heard big companies claim they're 100% renewable through something called annual matching. What that means is, over a whole year, they buy enough renewable energy credits to match their total usage. But think about it. On a Tuesday night when the wind isn't blowing, their data center is still pulling power from a grid that might be burning natural gas. The real goal, the holy grail, is 24/7 carbon-free energy, or CFE. And that means matching your energy use with clean power, hour by hour, in the same local region. No fossil fuels. Ever. And let me tell you, that is incredibly hard to do. Why? Well, because the sun doesn't always shine, and the wind doesn't always blow. To get to true 24/7 CFE, you can't just rely on solar and wind.
You need this whole portfolio of clean, stable, what they call baseload power sources, things like geothermal, hydropower, or even next-gen nuclear, plus just massive amounts of battery storage to fill in all the gaps. It's a gigantic technical and financial challenge.
Okay, so let's move from the power grid to what's happening inside the data center itself. Section 3, a revolution in cooling. All that computing generates an insane amount of heat, and getting rid of that heat is one of the single biggest energy drains and engineering headaches in the entire industry.
For decades, we've cooled data centers with, giant air conditioners, just blowing cold air. But we are hitting a fundamental wall of physics. The chips we use for AI and supercomputing are packed so tightly and run so incredibly hot that air just can't move the heat away fast enough. Once you get above a certain power density, we're talking about 30 kilowatts in a single rack, air cooling just plain stops working. The chips have to slow themselves down just to keep from melting.
And this is where liquid cooling comes into the picture. As you can see from this table, it's not a one-size-fits-all thing. You have direct-to-chip cooling, which is basically piping liquid directly onto the hottest parts of the processor. And then, for the most extreme high-power setups, you have immersion cooling, where you literally dunk the entire server into a bath of non-conductive fluid. These methods are way more efficient, but yeah, they come with new challenges, like the risk of leaks and much trickier maintenance.
So, we've covered power and cooling. Now we're on to the third front. And honestly, this is where things get really clever. Section 4, algorithms versus carbon. This is all about using software and smart code as a powerful weapon to slash emissions without having to build a single new thing. Check this out. It's a brilliant concept called temporal shifting. So imagine you have a huge but not super urgent task, like training a new AI model. A carbon-aware system checks the local power grid and sees, whoa, it's running on a lot of dirty energy right now. So it just automatically pauses your job. Then hours later, when the wind picks up and the grid is flooded with cheap, clean energy, the system automatically fires your job back up. You get the exact same result but with a way smaller carbon footprint. It's genius.
So, temporal shifting is one awesome tool. Another is geographic scheduling. So if the grid is dirty in Virginia, the system can just automatically zap your job over to a data center in Iowa where the wind is blowing. And this is all part of a much bigger idea called sustainable software engineering, which is basically about writing code from day one to be as lean and efficient as possible. This is the demand side of the puzzle that helps make that whole 24/7 clean energy goal actually work.
But even if we totally solve power, cooling, and code, there's still a fourth, and often completely overlooked front in this battle. Section 5, hardware's hidden footprint. This isn't about the cost of running the servers, it's about the cost of creating them in the first place.
And this brings us to this tricky economic idea called Jevons paradox. It's a little counterintuitive, but the paradox is that as technology gets more efficient and cheaper, we just end up using way more of it. Making computing faster doesn't just mean we do the same old stuff with less energy. It means we invent brand new, more demanding things to do, which means we have to build more and more hardware, which can actually cancel out all the efficiency gains we just made.
And that's why this term is so critical, embodied carbon. This is the total carbon footprint of a server before you ever even plug it in. It includes everything from mining the raw materials to the energy-guzzling factories that make the chips to shipping it all over the planet. For a lot of electronics, the embodied carbon is a massive chunk of its total lifetime impact on the environment.
So what's the answer to this embodied carbon problem? It's something called the circular economy. It's a simple but really powerful idea with 3 steps. First, reduce. Just use fewer new materials to begin with. Second, reuse. Design servers to be easily repaired and upgraded instead of just thrown away. And finally, for anything that can't be reused, you recycle it responsibly. It's all about breaking that old take, make, dispose cycle for good. Okay, let's bring all these different pieces together. Section 6, building the green cloud. This isn't about picking just one of these solutions. It's about creating a single, holistic strategy, people are starting to call it green ops, that weaves all 4 of these fronts together into one cohesive plan for a sustainable digital future.
And this isn't just some vague dream for the future. There's a pretty clear roadmap. In the short term, you focus on the software stuff. Track your skewer religiously and start using carbon-aware scheduling. Then, in the medium term, you pivot your infrastructure. Make liquid cooling the standard for all new AI systems, and start piloting true 24/7 clean energy projects. And the long-term goal? That's full circularity in the supply chain, and making data centers a truly integrated part of a clean energy grid.
So here's the bottom line. We have the technology. We have the strategies to build a dramatically cleaner cloud. We can measure carbon with CUE, we can chase 24/7 clean energy, we can revolutionize cooling with liquids, and we can use smart algorithms to dodge emissions. But this all leads to one final massive question. We are creating these amazing tools for sustainability, but at the exact same time, we're creating a practically infinite demand for more and more computing. So the real challenge is this: can our ingenuity keep pace with our own insatiable digital appetite? Thanks for watching.